On a rainy October afternoon in Parkins, Texas, Mrs. AC steps off a textured restaurant floor mat onto wet tile. In a fraction of a second, her feet shoot forward. Let's freeze the frame right here, with her suspended in midair. To understand why she is about to hit the floor, we have to conduct a forensic teardown of the biological systems that failed her in milliseconds. Walking is an interconnected sequence of synchronized movements that relies on a specific set of environmental expectations. The fundamental unit of walking is the gait cycle, requiring the sequential activation of body segments from the hip to the toe. This 100% gait cycle diagram maps the body's transition from single leg support into double leg support. Mechanical vulnerability peaks right here, at the bottom of the V, where the swing leg becomes the stance leg. The cycle requires a transfer of momentum that depends on split-second timing. The hardware powering that swing leg relies on a complex structural design. This is the kinetic chain. It operates on biotensegrity, where bones resist compression, while viscoelastic muscular pathways provide constant elastic tension to the system. On a microscopic level, these muscles act as actuators, contracting as protein filaments slide past one another to generate movement. The brain coordinates this movement through reciprocal inhibition, signaling antagonist muscles to relax so the agonist muscles can extend the limb. This hardware is mechanical. It functions solely based on the specific operating instructions it receives from the central nervous system. Those instructions originate in the cerebellum, the software governing the physical machine. Standard feedback systems like a home thermostat are too slow to keep a human upright. By the time the brain processed a slipping signal through a simple feedback loop, the body would already be on the ground. Instead, the cerebellum uses a feed-forward internal model. It predicts ground conditions based on past steps and visual cues before the foot even lands. It calculates the required coefficient of friction, or RCOF, the minimum amount of grip needed to safely arrest forward momentum upon heel contact. Because Mrs. AC was walking on a high-friction mat, her cerebellum programmed the RCOF for a dry surface, failing to account for the wet tile ahead. As we return to the timeline, her heel enters the final 10% of the swing phase, millimeters above the tile. This model shows the body's center of gravity moving forward at 1.6 meters per second. To land safely, the heel must slow down. As the foot approaches the floor, horizontal velocity should drop to 0.4 meters per second, with vertical speed slowing to 0.05. Heel contact occurs on the wet tile, where the actual friction available is lower than the brain's predicted RCOF. The ratio of horizontal to vertical forces is disrupted. Without enough friction to oppose the forward force, the heel continues to slide. The slip is a data mismatch. Physical reality has violated the brain's internal prediction. Immediately after the slip, proprioceptors signal the central nervous system that the limb is no longer where the internal model predicted it would be. The brain initiates a reactive recovery protocol, attempting to fire massive co-contractions in the leg muscles to stabilize the joint. The goal of this override is to pull the center of gravity back within the limits of stability. Because the tactile warning from the wet floor arrived too late, the muscular response is outmatched by the body's existing momentum. Gravity wins, and Mrs. AC hits the floor. This was an environmental failure. By not extending the mats to the carpeted area, the restaurant deprived her brain of the tactile cues required to update its friction requirements. Human walking is a series of billions of subconscious calculations. We are executing a continuous, controlled forward fall, held together by a prediction engine that assumes the ground will remain stable.